Think of 3i Atlas as a message in a bottle that's been drifting through the cosmic ocean for eons, except the message is written entirely in chemical whispers and spectral signatures. After combing through every study conducted on this interstellar visitor, from initial discovery observations to detailed compositional analysis spanning months of telescope time, I've assembled the most complete picture yet of what this alien chemistry is trying to tell us. The research reveals a comet unlike any we've seen before, carrying ingredients mixed under conditions that shouldn't exist according to our current understanding. But here's the twist that kept me awake parsing through scientific papers. One finding buried deep in the spectral analysis suggests this visitor might be carrying evidence of planetary formation processes we never knew existed. The implications are staggering, and by the end, you'll understand why this humble wanderer represents one of the most important scientific discoveries of our time. Part 1. A Visitor from the Stars. On July 1st, 2025, the Atlas survey in Chile detected something that stunned astronomers worldwide. A fragment of another star system hurtling through our cosmic neighborhood at 58 kilometers per second. This wasn't just another asteroid or comet from our own solar system's leftovers. This was 3i Atlas, the third confirmed interstellar object to visit our corner of the galaxy. But here's where the story gets interesting. Unlike its predecessors, this visitor carried secrets written in an alien chemistry that would challenge everything we thought we knew about how comets form in the cosmos. 3i Atlas arrived with credentials that marked it unmistakably as an outsider. Its hyperbolic orbit showed an eccentricity of approximately 6.1, a mathematical signature that screams, "I don't belong here." Objects bound to our Sun have eccentricities less than 1. Anything higher means they're just passing through, carrying the gravitational memories of distant stars. The timing of its discovery couldn't have been more perfect for scientific study. Perihelion, its closest approach to our Sun, would occur around October 30th, 2025, at approximately 1.4 astronomical units. That's just beyond Mars's orbit, close enough for detailed observations but far enough to avoid the Sun's overwhelming glare. Even better, its path would take it within 1.8 astronomical units of Earth and provide a spectacular flyby of Mars on October 3rd, 2025, passing within 30 million kilometers of the red planet. Let's be crystal clear about one thing that had everyone from NASA to amateur astronomers concerned. This object poses absolutely no threat to Earth. Its trajectory is well mapped, predictable, and safely distant. But what makes 3i Atlas truly fascinating isn't its path, it's what it's made of. To understand why this matters, we need to remember its predecessors. 1i/Oumuamua, discovered in 2017, was the first confirmed interstellar visitor. It showed bizarre non-gravitational acceleration with no visible coma, no dust or gas tail that would explain the force pushing it off course. Scientists proposed everything from hydrogen outgassing to exotic ice compositions to explain its mysterious behavior. Some even suggested more speculative origins, though the evidence never supported such claims. 2i/Borisov, found in 2019, was more cooperative. It behaved like a classic comet, developing a beautiful coma rich in carbon monoxide as it approached the Sun. But even Borisov was chemically unusual. Its carbon monoxide content was far higher than typical solar system comets, hinting that interstellar space might cook up comets with entirely different recipes. Now we had 3i Atlas, and early observations suggested it might split the difference between its enigmatic cousins. It was clearly active, developing a visible coma of dust and gas, but its composition would prove to be something else entirely. This is where the stakes become apparent. Interstellar objects offer us a unique opportunity. They're essentially free sample returns from other star systems. Every spectrum we capture, every chemical signature we decode, tells us something about planetary formation processes that occurred light years away and billions of years ago. We get to read the chemistry of alien worlds without ever leaving our own solar system. But here's the catch. The observation window is cruelly short. These visitors spend months or years approaching, give us weeks or months of prime observation time, then disappear into the outer solar system forever. There are no second chances, no follow-up missions, no opportunities to go back and check our work. It's a one-shot deal that requires coordinating telescopes around the globe and in space, racing against the clock as our target moves farther away each day. The Rubin Observatory, still in its commissioning phase, had already begun tracking 3I Atlas during its approach. This was a preview of things to come, a new generation of sky surveys that will spot interstellar objects earlier and farther out, giving us more time to study these cosmic messengers before they vanish into the dark. Early observations raised an intriguing question that would drive much of the scientific investigation to come. What if 3I Atlas's chemistry could challenge our fundamental understanding of how and where comets form? Not just in our solar system, but in the galaxy itself. What if this visitor carried evidence of formation conditions unlike anything we'd ever seen? The ground-based telescopes were already swinging toward its position. Space-based observatories were queuing up observation plans. Spectrographs were being calibrated to catch the faintest whispers of alien chemistry. The race was on to decode the secrets of 3I Atlas before it slipped away into interstellar space, carrying its mysteries back to the cosmic deep. And, as we'll discover, those secrets would prove to be more alien than anyone expected. The chemical signature hiding in 3I Atlas would rewrite our assumptions about comet formation and force us to reconsider what we thought we knew about the building blocks of planetary systems. But first, astronomers had to turn their instruments skyward and see what this visitor was willing to reveal. The stage was set for a cosmic detective story that would unfold in real time, with clues scattered across the electromagnetic spectrum and evidence that would challenge our most basic assumptions about how the universe builds worlds. Part 2. First Eyes on the Object. When the first telescopes locked onto 3I Atlas in early July 2025, astronomers expected to see familiar signatures, the chemical fingerprints that comets have been leaving across the galaxy for billions of years. What they found instead was the beginning of a puzzle that would take months to solve. The Very Large Telescope in Chile, armed with its MUSE instrument, captured the first detailed spectrum on July 3rd, just 2 days after discovery. The team led by Opitum peered through the telescope's sophisticated optics and found something oddly quiet. The spectrum showed a distinctly red, featureless continuum, the signature of sunlight scattered by dust particles in the comet's coma. But where were the gas lines that should have been shouting the comet's chemical identity to anyone willing to listen? This wasn't entirely unprecedented. Comets can be notoriously shy about revealing their gas content, especially when observed from great distances. But 3I Atlas was clearly active. It had a visible coma, proving that something was sublimating from its nucleus as solar heating increased. The question was, what? The X-Shooter instrument, operated by Alvarez Candel and collaborators, extended the spectral coverage from 300 to 2500 nanometers, painting a more complete picture of the object's color and continuum properties. Again, the observations were dominated by dust, scattered sunlight with a characteristic reddish tint that suggested the presence of complex organic materials or iron-bearing minerals. Still, the gas lines remained elusive. Meanwhile, the infrared telescope facility in Hawaii joined the hunt. Carretta and colleagues used the SPECS instrument to probe the near-infrared portion of the spectrum, confirming the reddish slope seen in optical observations, approximately 10% per 1,000 angstroms. This is the kind of measurement that makes astronomers scratch their heads and reach for more coffee. The color was definitely unusual, but without gas lines to provide chemical context, it remained largely mysterious. The Gran Telescopio Canarias in Spain's Canary Islands added another piece to the puzzle. De la Fuente Marcos and their team managed to extract evidence for rotation with a period of approximately 16.8 hours, while confirming the presence of a conspicuous dust coma. They also placed the object within its proper dynamical context, confirming that its orbital characteristics were indeed consistent with an interstellar origin. From Japan, Beniyama and collaborators contributed visible spectrophotometry that placed 3I Atlas's color indices as slightly redder than D-type asteroids, a class of objects rich in carbon and organic materials. Their work called for continued monitoring as the comet approached perihelion, recognizing that composition could evolve dramatically as solar heating intensified. By mid-July, a clear picture was emerging from these early observations. 3I Atlas exhibited a strong dust continuum with weak or entirely absent gas signatures. This was puzzling for several reasons. The object was clearly active at approximately 4 astronomical units from the Sun, a distance where water ice should be sublimating vigorously if it were present in typical abundances. Yet the characteristic signatures of water-derived gases were nowhere to be found. This placed 3I Atlas in an interesting position relative to its interstellar cousins. 2I/Borisov had shown classic comet features almost immediately upon discovery, developing a robust coma with strong carbon monoxide emission that marked it as distinctly different from solar system comets. 1I/Oumuamua, on the other hand, showed no detectable gas emission at all, leading to years of debate about its composition and the source of its non-gravitational acceleration. 3I Atlas seemed to occupy a middle ground, clearly active like Borisov, but keeping its chemical cards close to its chest like Oumuamua. The dust was there, the activity was there, but the gases that should have been screaming the object's identity across the electromagnetic spectrum were remarkably quiet. This raised an intriguing question that would drive much of the subsequent observation campaign. Was the reddish color they were seeing a property of the comet's surface materials, or was it the result of dust grain effects in the coma? Different grain sizes, compositions, and illumination geometries can dramatically affect the observed colors, making it difficult to separate intrinsic surface properties from coma contamination effects. The early non-detection of typical comet gases also opened up several possibilities. Perhaps 3I Atlas was simply too far from the Sun for significant gas production. Perhaps it had an unusual surface composition that preferentially released dust over gas. Or perhaps, and this would prove to be the most intriguing possibility, it was releasing gases, but not the ones astronomers were looking for. As July turned to August, the observation teams prepared to dig deeper. The initial reconnaissance had established that 3I Atlas was active, reddish, and rotating with a period of approximately 17 hours. But the real chemistry, the alien recipe that would make this interstellar visitor unique among its kind, remained hidden in wavelength ranges that these early observations couldn't access. The dust-dominated spectra were telling a story, but it was only the first chapter. Soon, other instruments operating in different parts of the electromagnetic spectrum would begin to reveal the chemical secrets that 3I Atlas had been carrying across interstellar space for millions of years. And those secrets would prove to be far more alien than anyone expected. Part 3. The Puzzle of the Coma. As August 2025 unfolded, astronomers found themselves staring at an increasingly perplexing mystery. 3I Atlas had all the visual hallmarks of an active comet, a clearly detectable coma extending thousands of kilometers from its nucleus, yet it stubbornly refused to reveal the chemical signatures that should have been obvious by this point in its approach to the Sun. The Very Large Telescope team had set stringent upper limits on the usual suspects. Hydroxyl radicals, the telltale signature of water sublimation, remained below their detection threshold at a production rate of less than 7.8 times 10 to the 23rd molecules per second at a heliocentric distance of 3.17 astronomical units. Cyanogen, carbon-2 molecules, carbon-3 chains, and the forbidden oxygen line at 6,300 angstroms, all the molecules that typically announce a comet's presence, were conspicuously absent from the spectra. This wasn't just unusual, it was downright puzzling. At 3 astronomical units from the Sun, water ice should be sublimating at a respectable rate, creating a detectable signature of hydroxyl radicals that ground-based telescopes could easily spot. The fact that these signatures were missing suggested either that 3I Atlas was remarkably water-poor or that something was masking the typical gas production signatures. The Hubble Space Telescope, with its unparalleled angular resolution and freedom from atmospheric interference, provided additional pieces to this cosmic jigsaw puzzle. Jewett and collaborators captured images that revealed the dust coma's structure in exquisite detail. The coma exhibited a distinctly asymmetric morphology, with dust preferentially distributed in the sunward direction, exactly what you'd expect from sublimating volatiles driving dust grains away from the nucleus. But here's where things got interesting. The Hubble observations were entirely consistent with faint gas production that was simply too weak to detect in ground-based spectra. The dust itself had to come from somewhere, and the most logical source was sublimating ices carrying dust grains along for the ride. The question remained, what kind of ices? Color measurements from multiple observatories showed intriguing variations that highlighted the challenges of studying these distant, fast-moving objects. Some teams reported color slopes of 20% per 1,000 angstroms, while others measured slightly more modest reddening. These discrepancies weren't necessarily contradictory. They could result from different filter systems, varying phase angles, or simply the inherent challenges of extracting precise photometry from a moving, extended object embedded in a crowded star field. One hypothesis began to emerge from the accumulating observations. Perhaps 3I Atlas was releasing large, icy dust grains rather than pure gas. These grains could carry water ice with them as they left the nucleus, sublimating slowly as they traveled through the coma. This process could mask the sharp gas lines that astronomers were expecting to see, while still producing the observed dust distribution and overall activity level. This grain source hypothesis had precedent in solar system comets, where icy dust particles have been observed to sublime over extended periods, creating what's sometimes called a distributed source of gas production. If 3I Atlas were producing particularly large or unusually composition icy grains, it could explain the apparent disconnect between clear activity and weak gas signatures. The comparison to 2I/Borisov was particularly instructive. Borisov had shown strong carbon monoxide and carbon dioxide signatures even at distances of 2 to 3 astronomical units from the Sun. These hypervolatile species sublime at much greater distances than water ice, making them easier to detect in distant comets. Some solar system comets also show distant activity driven by these exotic ices, so 3I Atlas's behavior wasn't entirely unprecedented, just unusual. As the observation teams compiled their results, a clear pattern emerged. They were seeing exactly what they expected from an active comet in terms of dust production and coma morphology, but the gas that should have been driving that activity remained stubbornly hidden. This mismatch between expected and observed signatures raised the stakes for the next phase of observations. The puzzle deepened when astronomers considered the broader implications. If 3I Atlas were truly gas-poor, it would represent a new class of interstellar object, something between the completely inactive 1I/Oumuamua and the gas-rich 2I/Borisov. But if gases were present but simply hiding in unexplored wavelength ranges, it suggested that interstellar comets might have compositional signatures unlike anything in our solar system. The solution to this puzzle would require looking beyond the traditional wavelengths where comet hunters typically search for gas signatures. Ultraviolet observations could reveal hydroxyl radicals with much greater sensitivity than optical telescopes. Infrared spectra could detect carbon dioxide, carbon monoxide, and other molecules that don't produce strong optical emission lines. As August progressed, observation teams prepared to deploy these more specialized capabilities. The mystery of 3I Atlas was about to deepen considerably as astronomers discovered that the comet wasn't gas-poor at all. It was simply speaking in a chemical dialect that no one had expected to hear from an interstellar visitor. The stage was set for revelations that would challenge fundamental assumptions about comet chemistry and force scientists to reconsider how these icy building blocks of planetary systems form in the cosmos. But first, they had to learn to listen to 3i Atlas in the right wavelengths. Part 4. The Ghost Before Discovery. Sometimes the most important discoveries hide in plain sight, waiting years for someone to notice them. Such was the case with 3i Atlas, which had been secretly performing for an audience of one NASA's transiting exoplanet survey satellite months before any human knew it existed. TESS wasn't built to hunt comets. This space-based observatory was designed to stare at stars, looking for the telltale dimming that occurs when planets pass in front of their host stars. But TESS has a unique capability. It watches large patches of sky continuously for 27 days at a time, building up an enormous archive of time-domain data that captures anything that changes brightness over time. Two independent teams realized they could use this archive to search for 3i Atlas before its official discovery date, a technique called recovery that can extend an object's observational baseline and provide crucial constraints on its orbit and physical properties. Feinstein, Noonan, and Seligman were the first to strike gold. They applied sophisticated image analysis techniques to test data, covering the period from May 7th to June 2nd, 2025. When 3i Atlas was still approximately 6.4 astronomical units from the Sun, well beyond the orbit of Jupiter. Using a technique called shift and stack, they aligned multiple TESS images to the predicted motion of the comet, then combined them to boost the signal-to-noise ratio. The result was remarkable, a clear detection of 3i Atlas showing brightness levels entirely consistent with its discovery magnitude in July. This wasn't just a technical triumph, it was evidence that the comet had been active for months before anyone knew it existed. The implications were immediately apparent. Traditional water ice sublimation becomes negligible at distances beyond about 3 astronomical units from the Sun. Yet here was 3i Atlas, clearly active at 6.4 astronomical units and showing no signs of dramatic brightness changes as it moved inward. This suggested that either hypervolatile species like carbon monoxide or carbon dioxide were driving the activity, or that some other mechanism was liberating dust and gas at these frigid distances. A second team, led by Martinez Palomera, independently confirmed and extended these results. Their analysis covered a broader time range and applied even more sophisticated techniques to account for TESS's complex pointing and calibration systematics. They not only confirmed the distant activity but also constructed light curves showing how the brightness evolved as 3i Atlas approached the inner solar system. The recovery detections established several important constraints. They confirmed that 3i Atlas had been producing a detectable dust coma for at least 2 months before discovery, with production rates that remained relatively stable over that period. They also helped refine the absolute magnitude measurements that are crucial for estimating the object's size and composition. Perhaps more importantly, the TESS observations provided a glimpse into the future of interstellar object science. TESS's all-sky monitoring capabilities, combined with its multi-year operational lifetime, create an unprecedented archive for discovering and characterizing transient phenomena. The same techniques used to find 3i Atlas could be applied to search for other interstellar visitors that might have passed through the solar system unnoticed. This connects directly to the promise of the Rubin Observatory, which will begin full-scale operations within the next few years. Rubin's combination of wide field coverage, deep sensitivity, and rapid cadence will likely discover interstellar objects much earlier in their approaches, providing months or years of lead time for detailed follow-up observations. The TESS recovery also highlighted an important technical point about working with space-based photometry. Stacked observations can bury systematic errors and create false positives if not handled carefully. Both teams took extensive precautions to validate their detections, cross-checking their methods and results to ensure they were seeing real astrophysical signals rather than data processing artifacts. But the most intriguing aspect of the TESS observations was what they suggested about 3I Atlas's composition and activity mechanisms. The fact that it was active at such large distances, combined with the relatively stable brightness over months of observation, painted a picture of an object with a substantial inventory of hypervolatile ices or unusually effective dust liberation mechanisms. This set up one of the central questions that would drive the remainder of the observation campaign. If 3I Atlas was active at 6 astronomical units, what was driving that activity? Carbon monoxide and carbon dioxide can sublime at those distances, but they're difficult to detect with ground-based optical telescopes. Dust liberation by subsurface gas pockets or grain impacts was possible, but would require specific physical conditions that weren't yet constrained by observations. The TESS recovery had revealed that 3I Atlas was far more active than its optical spectra suggested. Somewhere in the ultraviolet or infrared parts of the electromagnetic spectrum, this interstellar visitor was broadcasting its chemical identity. The challenge for astronomers was learning how to tune in to the right frequency. As summer 2025 progressed, observation teams prepared to deploy the most sensitive gas detection capabilities available to science. The answer to 3I Atlas's activity puzzle was about to emerge from wavelength ranges that ground-based telescopes couldn't access, and those answers would prove more alien than anyone expected. Part 5. Hubble's Glimpse. When the Hubble Space Telescope turned its exquisite optics toward 3I Atlas in August 2025, it captured something that ground-based telescopes had been struggling to quantify: clear, unambiguous evidence of ongoing activity that told a story about dust, gas, and the delicate dance between sublimating ice and escaping particles. At approximately 3.8 astronomical units from the Sun, 3I Atlas was far enough away that its coma remained relatively compact, perfect for Hubble's high angular resolution capabilities. Jewett and collaborators used the Space Telescope's advanced camera for surveys to peer through the solar system's debris and capture images that revealed the comet's secrets in unprecedented detail. The most striking feature was the coma's asymmetry. Dust particles extended preferentially in the sunward direction, creating a fan-shaped distribution that pointed directly toward the source of illumination and heating. This wasn't unusual for comets. Solar radiation pressure and gas drag typically push dust grains into characteristic tail structures, but the clarity of Hubble's images allowed the team to quantify these effects with remarkable precision. Using sophisticated modeling techniques, the researchers estimated that 3I Atlas was losing dust at a rate of approximately 1 kilogram per second, assuming typical grain sizes in the micrometer range. This may sound modest, but sustained over months of activity, it represents millions of kilograms of material stripped away from the comet's nucleus and scattered throughout the inner solar system. The dust mass loss rate provided crucial constraints for understanding the underlying gas production that must be driving the activity. Dust grains don't spontaneously leap off comet nuclei. They require gas flow to lift them against the weak but persistent gravitational pull of the nucleus. The amount of dust being produced gave astronomers a handle on the minimum gas production rate, even if that gas remained invisible to optical telescopes. Hubble's observations also helped resolve one of the persistent puzzles from ground-based spectroscopy. How could 3I Atlas show clear activity while producing such weak optical gas signatures? The answer appeared to lie in the wavelength ranges being observed and the physical conditions in the coma. At 3.8 astronomical units from the Sun, the comet was still relatively cold, and the gas densities in the coma were probably quite low. Under these conditions, the collision rates between gas molecules and electrons are insufficient to produce strong optical emission lines through the fluorescence processes that typically make comet gases visible to ground-based telescopes. However, other molecules, particularly those that can be excited by solar ultraviolet radiation, might still be detectable with the right instruments. Hydroxyl radicals, the primary photodissociation product of water molecules, absorbs strongly in the ultraviolet and could potentially be detected even when parent water molecules remained invisible in optical wavelengths. This insight pointed toward the next phase of the observation campaign. While Hubble had confirmed that 3I Atlas was definitely active and probably gas-rich, it would take specialized ultraviolet and infrared observations to decode the chemical signatures hiding in the coma. The geometric constraints provided by Hubble's high-resolution images were also crucial for understanding the nucleus itself. By carefully modeling the dust distribution and accounting for the effects of solar radiation pressure and gas drag, astronomers could work backward to constrain the size and activity patterns on the nucleus surface. These calculations suggested that 3I Atlas's nucleus was probably several kilometers in diameter, comparable to or larger than 2I/Borisov, and definitely larger than the estimated size of 1I/Oumuamua. However, these size estimates remained model-dependent, relying on assumptions about surface reflectivity, dust production efficiency, and activity distribution that couldn't be directly verified. The rotation period measured by ground-based observers, approximately 16 to 17 hours, fit well with Hubble's coma structure observations. A rotating nucleus with asymmetric activity patterns could explain some of the time-variable features seen in the dust distribution, though the coma itself was probably too extended and long-lived to show sharp rotational signatures. Perhaps most importantly, Hubble's observations provided a clear transition point in the 3I Atlas story. The Space Telescope had confirmed that this interstellar visitor was behaving like a classic comet in terms of dust production and coma development. The mysterious aspect wasn't whether it was active, it clearly was, but rather what chemical species were driving that activity. The stage was now set for the revelation that would transform 3I Atlas from a puzzling but relatively mundane interstellar comet into one of the most chemically exotic objects ever observed. Ground-based optical telescopes had done their job of characterizing the dust and overall activity level. Hubble had confirmed the basic physics of gas-driven dust production. Now it was time for ultraviolet and infrared observations to reveal the alien chemistry that 3I Atlas had been carrying across interstellar space, chemistry that would challenge fundamental assumptions about how comets form and evolve in the galaxy. The water was about to turn on, but as astronomers would soon discover, it wasn't the only thing flowing from this mysterious visitor from the stars. Part 6. Water Awakens. On July 31, 2025, the Swift Gamma-Ray Burst mission, a satellite designed to detect the universe's most violent explosions, quietly revolutionized our understanding of 3I Atlas with one of the most sensitive water detections ever made in an interstellar comet. Swift's ultraviolet optical telescope wasn't hunting for gamma-ray bursts that day. Instead, Xing and collaborators had commandeered the spacecraft to peer at 3I Atlas in ultraviolet wavelengths, searching for the hydroxyl radical signature that had eluded ground-based observers for weeks. What they found would rewrite the narrative of this interstellar visitor. The detection was unambiguous, hydroxyl radicals glowing at 3,808 angstroms, the unmistakable signature of water molecules being torn apart by solar ultraviolet radiation. The team measured a water production rate of approximately 1.3 times 10 to the 27th molecules per second, equivalent to about 40 kilograms per second of pure water vapor streaming away from the nucleus. This was remarkable for several reasons. First, sustained water production at 40 kilograms per second represents a significant fraction of the total mass budget for a kilometer-scale comet nucleus. Second, and more importantly, this level of water activity at 3.51 astronomical units from the Sun was highly unusual for any comet, let alone one from interstellar space. Most solar system comets show minimal water activity beyond 3 astronomical units. The sublimation temperature of water ice requires substantial solar heating to drive significant gas production, which typically doesn't occur until comets approach within about 2.5 astronomical units of the Sun. Yet here was 3I Atlas, pumping out water vapor at distances where most comets remain dormant. The implications were immediately apparent to Yang and colleagues, who had been studying the comet's near-infrared properties with the Gemini multi-object spectrograph and the SPECS instrument at the Infrared Telescope facility. Their data showed evidence for large icy grains in the coma, particles that could carry water ice with them as they escaped the nucleus, providing an extended source of hydroxyl production as they slowly sublimated in the vacuum of space. This distributed source model could explain several puzzling aspects of 3I Atlas's behavior. Large icy grains would sublime more slowly than pure gas, extending the production over larger volumes of the coma and potentially masking sharp emission lines that ground-based telescopes were expecting to see. The grains could also carry other volatile species, creating a complex chemical environment that wouldn't match the simple gas production models typically applied to comet observations. The swift detection also helped resolve the apparent contradiction between clear dust activity and weak gas signatures that had puzzled astronomers throughout July. Ultraviolet wavelengths are simply more sensitive to hydroxyl radicals than optical telescopes, even when the parent water molecules remain difficult to detect directly. The gas had been there all along, astronomers just hadn't been looking in the right wavelength range. But Swift's water detection raised as many questions as it answered. If 3I Atlas was producing water at 40 kilograms per second, where was the corresponding signal from other typical comet volatiles? Carbon-based molecules like cyanogen and carbon-2 should have been easily detectable at this activity level, yet they remained conspicuously absent from optical spectra. This suggested that 3I Atlas might have an unusual volatile inventory compared to typical solar system comets. Perhaps it formed in a chemical environment that favored water ice formation while suppressing carbon-bearing species. Or perhaps other volatile species were present but hidden in wavelength ranges that hadn't yet been explored. The water detection also provided crucial constraints for understanding the comet's thermal properties and surface composition. The fact that water sublimation was occurring at such large distances suggested either an unusually dark surface that could absorb solar radiation efficiently, or the presence of subsurface ice deposits that could be liberated by other processes. Some solar system comets showed distant water activity driven by stored thermal energy or crystallization processes in amorphous ice deposits. If 3I Atlas had formed under conditions that created particularly reactive ice phases, it could explain the distant activity without requiring exotic chemical compositions. However, the most intriguing possibility was that water wasn't the dominant volatile species in 3I Atlas at all. The Swift observations had confirmed that water was present and active, but they hadn't ruled out the possibility that other gases were present in even higher concentrations. Carbon dioxide and carbon monoxide, for example, can sublime at much greater distances from the Sun and don't produce strong optical emission lines that ground-based telescopes can easily detect. If 3I Atlas were rich in these hypervolatile species, it could explain both the distant activity and the unusual spectroscopic properties observed so far. As August 2025 progressed, observation teams prepared to test this hypothesis using the most sensitive infrared spectroscopy capabilities available to science. The James Webb Space Telescope, with its unprecedented sensitivity to molecular signatures in the 2 to 28 micrometer wavelength range, was preparing to turn its golden mirrors toward 3I Atlas. The water discovery had confirmed that this interstellar visitor was chemically active and probably carrying a substantial inventory of volatile species. But the real surprise, a chemical signature so alien that it would challenge fundamental assumptions about comet formation, was still waiting to be discovered in the infrared depths of 3I Atlas's hidden composition. Part 7. The Koto Surprise. On August 25, 2025, the James Webb Space Telescope delivered a revelation that would fundamentally alter our understanding of interstellar comet chemistry. Using its near-infrared spectrograph, Cordner and the international JWST team peered into the 2 to 5 micrometer wavelength range and discovered something that shouldn't have been possible. 3I Atlas wasn't just producing water vapor. It was absolutely dominated by carbon dioxide at a ratio that defied everything astronomers thought they knew about comet formation. The JWST spectrum was a masterclass in alien chemistry. Carbon dioxide emission lines blazed across multiple infrared bands, accompanied by water vapor, carbon monoxide, carbonyl sulfide, and even crystalline water ice suspended in the coma. But the numbers that emerged from careful spectroscopic analysis were staggering. The carbon dioxide to water ratio was approximately 8 to 1, plus or minus 1. To put this in perspective, typical solar system comets show carbon dioxide to water ratios of around 0.1 to 0.5. The most carbon dioxide-rich comet previously known, C/2016 R2, reached ratios of about 2 to 1 under specific conditions. 3I Atlas was producing carbon dioxide at levels that placed it in a class essentially by itself. This wasn't a subtle effect or a marginal detection. The JWST spectrum showed carbon dioxide emission that was 8 times stronger than water vapor emission from the same volume of coma. This interstellar visitor was essentially a carbon dioxide comet with water as a minor constituent, exactly the opposite of what astronomers expected based on decades of solar system comet observations. The discovery was independently supported by early results from SPHERICS, NASA's newest space-based all-sky survey mission. Multispectral observations at 3.3 and 3.1 astronomical units confirmed both carbon dioxide and water ice signatures, providing additional evidence that this unusual chemistry was sustained over time as the comet approached the Sun. The implications for comet formation theory were immediately apparent. In our solar system, carbon dioxide ice typically forms farther from the Sun than water ice, requiring colder temperatures and different chemical environments. A comet with such extreme carbon dioxide enrichment could have formed near a carbon dioxide ice line in its parent system, or could have experienced radically different processing conditions than anything in our local cosmic neighborhood. The JWST observations also revealed exquisite details about the gas production geometry. The carbon dioxide emission showed clear evidence for sunward outgassing, with the strongest signals coming from the dayside hemisphere of the nucleus, where solar heating was most intense. This confirmed that sublimation physics, not exotic processes, was driving the activity, but the composition being sublimated was unlike anything previously seen. Carbonyl sulfide, a molecule rarely detected in solar system comets, added another layer of chemical exoticism to 3I Atlas. This sulfur-bearing species is typically associated with high-temperature chemistry or unusual processing conditions, suggesting that the comet's formation environment involved chemical pathways that don't occur in our solar system's comet-forming regions. The detection of crystalline water ice in the coma provided additional clues about the physical processes occurring as 3I Atlas approached the Sun. Crystalline ice forms when amorphous ice is heated, releasing stored energy and potentially triggering enhanced activity. The presence of both ice phases suggested a complex thermal environment within the coma, but the carbon dioxide domination raised profound questions about the swift ultraviolet observations from late July. If carbon dioxide was the primary volatile species, why had water appeared so prominently in ultraviolet wavelengths? The answer seemed to lie in the complex physics of gas production and excitation in comet comae. Carbon dioxide doesn't produce strong ultraviolet emission lines that space-based telescopes can easily detect. Water vapor, while present in much smaller quantities, is much more easily excited by solar ultraviolet radiation and produces the hydroxyl signatures that Swift had observed. This meant that the early ultraviolet detections had been seeing the minor water component while completely missing the dominant carbon dioxide inventory. The JWST discovery also helped explain the unusual activity patterns that had puzzled astronomers since discovery. Carbon dioxide can sublime at much greater distances from the Sun than water ice, which explained why TESS had detected activity at 6.4 astronomical units. The comet had been sublimating its primary volatile inventory from the moment it entered the outer solar system. This revelation fundamentally changed the interpretation of every previous observation. The dust-dominated early spectra weren't evidence of a gas-poor object. They were evidence of a comet producing gases that don't emit strongly in optical wavelengths. The weak water signatures weren't evidence of water scarcity. They were evidence that water was a minor component of an exotic chemical inventory. The formation implications were staggering. If 3I Atlas had indeed formed in a carbon dioxide-rich environment, it suggested formation conditions unlike anything in our solar system. Perhaps it originated in a system with a different stellar type, where the carbon dioxide ice line was located at different distances from the star. Perhaps it formed during an earlier epoch of galactic evolution, when the interstellar medium had different chemical properties. Alternatively, the extreme carbon dioxide enrichment could be the result of processing during its millions of years of interstellar travel. Cosmic ray bombardment, exposure to the interstellar radiation field, or interactions with interstellar dust could potentially alter surface chemistry over geological timescales. However, such processing would typically destroy volatile species rather than concentrating them, making this explanation less likely. The JWS team was careful to note that their observations represented a single epoch snapshot of 3I Atlas's composition. Comet chemistry can evolve dramatically as objects approach the Sun, with different volatile species becoming active at different distances. The 8:1 carbon dioxide to water ratio observed in late August might not represent the comet's bulk composition. It could simply reflect the relative ease with which these species sublime under the conditions present at 3.1 astronomical units. This caveat set up one of the most important questions for the remainder of the observation campaign. Would the carbon dioxide to water ratio remain constant as 3I Atlas approached perihelion, or would increasing solar heating activate additional water ice deposits that could shift the balance? The answer would have profound implications for understanding not just 3I Atlas, but interstellar comet formation in general. If the extreme carbon dioxide enrichment persisted throughout the comet's perihelion passage, it would suggest truly exotic formation conditions. If the ratio evolved toward more typical values, it might indicate layered composition or unusual thermal processing. But even as astronomers digested the implications of JWST's carbon dioxide surprise, other telescopes were making discoveries that would add even more layers of chemical exoticism to 3I Atlas's already bizarre profile. The interstellar visitor was about to reveal molecular signatures that would challenge fundamental assumptions about the periodic table's representation in distant comet-forming regions. Part 8. The strange chemistry. While JWST was revolutionizing our understanding of 3I Atlas's volatile inventory, ground-based telescopes continued their patient vigil in optical wavelengths, watching for the delayed onset of more familiar comet chemistry. What they discovered would add yet another layer of exoticism to an already unprecedented interstellar visitor. The Very Large Telescope's second major spectroscopic campaign, led by Rahat Gaonkar and collaborators, began detecting optical emission lines in late August as 3I Atlas passed within 2.85 astronomical units of the Sun. But the chemistry they found was as peculiar as everything else about this cosmic wanderer. Nickel, atomic nickel, was blazing across multiple optical wavelengths with an intensity that defied conventional comet chemistry models. The team detected numerous nickel-1 emission lines while iron-1 lines remained stubbornly below detection limits. This was backwards from what anyone expected. In typical cosmic environments, iron is far more abundant than nickel, and both elements should appear together if they're being released from metallic phases in the comet nucleus. The production rate measurements told the story in stark quantitative terms. Nickel was being produced at approximately 4.7 times 10 to the 22nd atoms per second, while iron remained undetectable despite being searched for with comparable sensitivity. The scaling of nickel production with heliocentric distance was equally puzzling, a steep power law with an exponent of negative 8.4, suggesting a highly temperature-sensitive release mechanism. Conventional models for metal release from comet nuclei typically invoke direct sublimation of metallic particles or metal-bearing sulfide minerals. These processes should release iron and nickel in roughly cosmic abundance ratios, not the extreme nickel enhancement observed in 3I Atlas. Something else was clearly happening. The most promising explanation involved photon-stimulated desorption or mild thermolysis of nickel-bearing organic compounds or nanophase materials embedded in the comet's nucleus. These processes could preferentially release nickel while leaving iron locked in more refractory phases, explaining the unusual abundance ratios observed. This hypothesis suggested that 3I Atlas contained organic materials with embedded metallic nanoparticles, structures that could form under specific chemical conditions in protoplanetary disks or through processing in the interstellar medium. The nickel could be incorporated into organic frameworks that would release the metal atoms when heated or exposed to intense solar ultraviolet radiation. Meanwhile, cyanogen finally made its appearance in the optical spectrum on August 21st. The McDonald Observatory campaign led by Salazar Manzano detected the CN radical at a production rate of approximately 4 times 10 to the 23rd molecules per second, a respectable detection that confirmed the presence of carbon-nitrogen chemistry in the coma. But even the cyanogen detection carried surprises. The carbon-2 to cyanogen ratio was extremely low, less than negative 1.05 in logarithmic units, indicating severe depletion of carbon chain molecules compared to typical solar system comets. This placed 3I Atlas among the most carbon chain depleted comets ever observed, rivaling some of the most unusual objects in the solar system's inventory. The combination of strong carbon dioxide emission from JWST observations and weak carbon chain emission from optical telescopes painted a picture of highly fractionated carbon chemistry. Carbon dioxide was abundant, cyanogen was present but not dominant, and longer carbon chains were severely depleted or absent entirely. This suggested formation or processing conditions that could build simple carbon-oxygen bonds while suppressing more complex carbon chemistry. The overall gas-to-dust ratio also appeared unusually low based on the McDonald Observatory observations. Most of the mass being lost from 3I Atlas was in the form of dust particles rather than gas molecules, despite the clear evidence for active sublimation from JWST and SWIFT observations. This could indicate either unusually efficient dust production mechanisms or an intrinsically dust-rich nucleus composition. Temporal variability added another layer of complexity to the chemical picture. Both nickel and cyanogen production showed evidence for day-to-day variations that couldn't be explained by simple changes in heliocentric distance or solar illumination geometry. These variations suggested either rotation-driven activity patterns on the nucleus surface or more complex chemical processes operating in the coma itself. The steep production scaling laws, nickel with a negative 8.4 power law, cyanogen with negative 9.4, indicated highly temperature-sensitive processes that would become dramatically more active as 3I Atlas approached perihelion. These steep scalings set up clear predictions for how the chemistry should evolve during the final approach to the Sun. By early September, a coherent but bizarre chemical picture was emerging. 3I Atlas was dominated by carbon dioxide, contained detectable water and carbon monoxide, showed unusual nickel chemistry without corresponding ion signatures, produced cyanogen, but was severely depleted in longer carbon chains, and exhibited a low gas-to-dust ratio despite clear evidence for active volatile sublimation. This combination of characteristics didn't match any known class of solar system comets. It suggested formation in an environment with chemical conditions unlike anything in our local cosmic neighborhood, or processing during interstellar travel that had fundamentally altered the comet's original composition. The comparisons to 2I/Borisov were particularly striking. Borisov had also shown unusual volatile ratios, particularly its extreme carbon monoxide enrichment, but its overall chemistry was at least broadly consistent with carbon monoxide-rich solar system comets. 3I Atlas was exhibiting chemical signatures that placed it in a category entirely its own. As astronomers digested these results, they couldn't help but draw parallels to the debates that had raged around 1I/Oumuamua. That first interstellar visitor had shown kinematic anomalies that challenged conventional explanations, leading to increasingly exotic hypotheses about its composition and origin. Now 3I Atlas was presenting chemical anomalies that were equally challenging to explain within the framework of conventional comet science. Part 9. Echoes of Oumuamua. The discovery of 3I Atlas's exotic chemistry inevitably drew comparisons to the most controversial interstellar object in recent memory, 1I/Oumuamua, the elongated visitor that had sparked years of scientific debate and captured the public imagination with its mysterious properties. 1I/Oumuamua, discovered in October 2017, had shown no detectable coma or gas production, despite exhibiting clear non-gravitational acceleration as it departed the solar system. This combination of properties, visible acceleration without visible outgassing, had challenged conventional explanations and led to increasingly creative hypotheses about its composition and nature. The scientific response to Oumuamua had been a masterclass in how astronomers reason under uncertainty. When conventional water-ice sublimation couldn't explain the observed acceleration, researchers proposed hydrogen gas outgassing from subsurface reservoirs. When hydrogen seemed insufficient, they suggested nitrogen ice sublimation similar to processes observed on Pluto. When nitrogen ice models faced their own challenges, some researchers proposed dust-driven radiation pressure effects or even more exotic scenarios. The debates around Oumuamua illustrated both the strengths and limitations of astronomical inference. With limited observational data and a rapidly departing target, scientists were forced to construct models based on indirect evidence and theoretical assumptions. Different research groups, working with the same data, reached dramatically different conclusions about the object's most basic properties. 3I Atlas presented a completely different type of mystery. Where Oumuamua had shown kinematic anomalies without chemical signatures, 3I Atlas displayed chemical anomalies with perfectly conventional kinematics. There were no claims of unusual acceleration, no debates about radiation pressure or exotic outgassing mechanisms. The physics was straightforward comet behavior, sublimation-driven activity producing gas and dust in response to solar heating. But the chemistry was unprecedented. The 8:1 carbon dioxide to water ratio, the nickel emission without iron, the carbon chain depletion, the distant activity, All of these signatures pointed to formation or processing conditions unlike anything in our solar system. The mystery wasn't how 3I Atlas was behaving, but what it was made of and where it had come from. This distinction was crucial for understanding how the scientific community would respond to 3I Atlas. Unlike Oumuamua, which required exotic physics to explain its behavior, 3I Atlas operated according to well-understood physical principles. The challenge was interpreting its chemical composition within the framework of planetary formation theory. However, the public attention surrounding interstellar objects had inevitably attracted more speculative interpretations. Hibbard, Crowell, and Loeb published a preprint suggesting that 3I Atlas might represent artificial technology rather than a natural comet. These authors argued that the unusual chemical signatures could be consistent with industrial processes or technological materials. It's important to emphasize that these technological hypotheses remained purely speculative and were not supported by the observational evidence available at the time. The JWST spectra, VLT detections, and swift observations were all entirely consistent with natural comet chemistry, albeit chemistry unlike anything previously observed. R.V. Loeb, who had been a prominent advocate for considering technological explanations for Oumuamua's anomalies, also commented on 3I Atlas's discovery. His commentary, posted on the Harvard-Smithsonian Center for Astrophysics website, acknowledged the unusual chemical signatures while noting that they didn't necessarily require artificial origins. The responsible approach to these speculative interpretations required separating entertaining possibilities from measured evidence. The carbon dioxide domination, nickel emission, and other chemical signatures observed by peer-reviewed instruments on world-class telescopes represented solid observational facts. The interpretation of those facts as evidence for technology rather than exotic natural chemistry remained unsupported by the available data. This distinction highlighted an important aspect of science communication in the age of social media and rapid information dissemination. Tabloid headlines and viral social media posts don't carry the same evidential weight as peer-reviewed publications or official NASA announcements. The most reliable information about 3I Atlas came from the scientific teams actually observing the object with calibrated instruments. The technological speculation served a useful purpose in demonstrating the truly exotic nature of 3I Atlas's chemistry. If the observed signatures were unusual enough to inspire hypotheses about artificial origins, they were certainly unusual enough to challenge conventional models of comet formation and evolution. But the more important question was what 3I Atlas's chemistry could teach us about natural processes in other star systems. The extreme carbon dioxide enrichment, the unusual metal ratios, the carbon chain depletion, all of these signatures pointed to chemical environments or formation conditions that don't exist in our solar system. Rather than evidence for technology, 3I Atlas might be evidence for the incredible diversity of planetary formation processes operating throughout the galaxy. Different stellar types, different disk temperatures, different chemical inventories in star-forming regions, all of these factors could contribute to building comets with compositions unlike anything in our local cosmic neighborhood. The comparison to Oumuamua also highlighted how much observational capability had improved between 2017 and 2025. Oumuamua's brief visit had caught the astronomical community largely unprepared, with limited telescope time and observational strategies developed on the fly. 3I Atlas, in contrast, was being observed with coordinated campaigns involving the most sophisticated instruments available to science. This improved observational approach was already paying dividends in terms of understanding interstellar object diversity. Where Oumuamua had remained largely enigmatic, 3I Atlas was revealing its secrets in exquisite detail. The question was no longer whether interstellar objects could be chemically unusual, it was how unusual they could be while remaining consistent with natural formation processes. Part 10. Where did it come from? As the chemical portrait of 3I Atlas grew more detailed and more bizarre, astronomers turned their attention to perhaps the most fundamental question of all: where in the galaxy could such an exotic object have formed? The answer would require combining cutting-edge galactic dynamics with theoretical models of planetary system formation, painting a picture of cosmic evolution spanning billions of years. Taylor and Seligman, publishing their kinematic analysis on July 10, 2025, had been among the first to tackle this question. Using sophisticated orbital integration techniques, they traced 3I Atlas's trajectory backward through galactic space, accounting for the gravitational influences of the Milky Way's stellar population, dark matter halo, and central supermassive black hole. Their results were striking. 3I Atlas appeared to have been wandering through interstellar space for approximately 3 to 11 billion years. This enormous age range reflected the inherent uncertainties in galactic dynamics calculations, but even the lower bound suggested that this interstellar visitor was ancient by any reasonable standard. More intriguingly, the kinematic analysis suggested that 3I Atlas likely originated from the galaxy's thick disk population, a component of older, more metal-poor stars that formed during the Milky Way's early evolutionary phases. This was a crucial clue for understanding the comet's exotic chemistry. Hopkins, working with the Tortar Oxford Galactic Evolution Model, provided additional context for these findings. The thick disk represents a stellar population that formed approximately 8 to 12 billion years ago, when the galaxy's chemical composition was significantly different from today's star-forming regions. Stars in this population are typically metal-poor compared to younger thin-disk stars, and they likely hosted protoplanetary disks with chemical inventories unlike anything seen in contemporary planet-forming systems. The connection to 3I Atlas's unusual chemistry began to make sense within this framework. A comet that formed 8 billion years ago in a metal-poor protoplanetary disk might indeed exhibit chemical signatures unlike anything in our 4.6 billion-year-old solar system. The carbon dioxide domination, the unusual metal ratios, the carbon chain depletion, all of these could reflect formation conditions that no longer exist in the modern galaxy. The JWST observations provided additional support for this ancient origin hypothesis. Carbon dioxide-rich compositions could result from formation near a carbon dioxide ice line in a protoplanetary disk with different temperature and chemical gradients than our solar nebula. Alternatively, the extreme carbon dioxide content could reflect radiation processing of organic materials over billions of years of interstellar travel. The thick disk origin scenario also helped explain some of the more subtle aspects of 3I Atlas's behavior. The swift observations had shown water production at unusually large distances from the Sun, possibly indicating the presence of amorphous ice phases that could be destabilized by cosmic ray processing during the comet's long interstellar journey. The presence of large icy grains in the coma, detected by Yang and colleagues, could also be a signature of ancient processing. Repeated thermal cycling, cosmic ray bombardment, and interactions with interstellar dust over geological timescales might create unusual ice structures that could explain the observed grain-size distributions and sublimation patterns. The velocity components measured by the Gran Telescopio Canarias team provided additional kinematic evidence for a thick disk origin. The U, V, and W velocity components were consistent with an object that had been moving on a highly inclined orbit with respect to the galactic plane, exactly what would be expected for a member of the thick disk population. However, the age and metallicity inferences came with important caveats. Galactic dynamics calculations become increasingly uncertain when extended over billions of years, and the assignment to specific stellar populations remains probabilistic rather than definitive. 3I Atlas could conceivably have originated from a young, metal-rich system and acquired its unusual chemistry through interstellar processing rather than primordial formation conditions. The population statistics implications were particularly exciting in the context of upcoming survey capabilities. The Rubin Observatory's Legacy Survey of Space and Time, scheduled to begin full operations within the next few years, should dramatically increase the rate of interstellar object discoveries. If the thick disk versus thin disk origin hypothesis could be tested with larger samples, it would provide unprecedented constraints on galactic chemical evolution and planetary formation processes. A population dominated by thick disk objects would suggest that most interstellar visitors are ancient relics from the galaxy's early phases of planet formation. A mixture of thick disk and thin disk objects would indicate ongoing ejection of comets from contemporary stellar systems. The relative proportions could reveal how planetary system architectures and ejection mechanisms have evolved over cosmic time. The formation environment constraints also had implications for understanding the diversity of exoplanetary systems. If 3I Atlas represented typical building blocks from ancient protoplanetary disks, it suggested that the chemical inventory available for planet formation has changed dramatically over the galaxy's history. Modern terrestrial planet formation models assume chemical compositions similar to our solar system's inventory. But if the building blocks were systematically different billions of years ago, more carbon dioxide rich, with unusual metal abundances, and depleted in complex carbon chemistry, it could fundamentally alter predictions for the atmospheres and surface compositions of ancient exoplanets. The thick disk origin scenario painted a picture of 3I Atlas as a cosmic time capsule, carrying chemical information about planetary formation processes that operated when the galaxy was young and chemically primitive. This interstellar visitor wasn't just an exotic curiosity, it was a direct sample of primordial comet-building chemistry, preserved in the deep freeze of interstellar space for billions of years. As 3I Atlas continued its approach toward perihelion, astronomers prepared to test whether this ancient chemistry would remain stable under intense solar heating, or whether proximity to our Sun would reveal additional layers of compositional complexity preserved from the galaxy's distant past. Part 11. Activity over time. As 3I Atlas swept through the inner solar system during September and October 2025, astronomers had the unprecedented opportunity to watch an interstellar comet's chemistry evolve in real time. The temporal evolution of gas and dust production provided crucial insights into the physical structure of this alien visitor and the processes governing its exotic behavior. Santana Ross and collaborators provided the most comprehensive view of the comet's evolving activity during its first month of observations. Their analysis revealed a rotation period of approximately 16.2 hours, with increasing dust production and systematically reddening colors as the comet approached the Sun. Dust mass loss estimates ranged from 0.3 to 4.2 kilograms per second, depending on assumptions about grain size distributions and optical properties. This temporal evolution painted a picture of a nucleus that was becoming more active as solar heating intensified, but the details revealed surprising complexity. Rather than simple monotonic increases in activity, 3I Atlas showed evidence for variable production rates that couldn't be explained solely by changing heliocentric distance or solar illumination geometry. The SOAR Observatory Photometry campaign, led by Frinker and colleagues, provided additional constraints on the rotation and activity patterns. Their near-discovery light curve measurements showed no clear rotational modulation due to coma contamination effects, but careful analysis revealed brightenings that could be explained by variable seeing conditions and contamination from nearby stars rather than intrinsic activity variations. This highlighted one of the persistent challenges in studying active comets, separating real astrophysical signals from instrumental and environmental effects. The extended coma makes photometry difficult by spreading light over larger areas than typical point sources, while the comet's motion against the stellar background creates additional complications for precise measurements. The McDonald Observatory cyanogen monitoring provided some of the clearest evidence for temporal evolution in gas production. Between August 8th and 17th, CN emission lines appeared and strengthened systematically, indicating that carbon-nitrogen chemistry was becoming more active as 3I Atlas moved from approximately 3.1 to 2.8 astronomical units from the Sun. The timing of this cyanogen onset was particularly interesting when compared to the earlier JWST carbon dioxide detections. Carbon dioxide had been active since at least late July at 3.5 astronomical units, while cyanogen didn't become detectable until mid-August at closer distances. This suggested different volatility thresholds for different chemical species, providing insights into the thermal structure and composition gradients within the nucleus. The VLT nickel monitoring revealed even more dramatic temporal evolution. The extremely steep production scaling, proportional to heliocentric distance to the negative 8.4 power, indicated a highly temperature-sensitive process that would become explosively active as the comet approached perihelion. This steep scaling was among the highest ever measured for any molecular species in any comet. These scaling laws provided testable predictions for how 3I Atlas's chemistry should evolve during its final approach to the Sun in late October. If the nickel release mechanism remained consistent, production rates should increase by more than 2 orders of magnitude between August observations and perihelion passage. The proposed nickel-carbonyl pathway offered a compelling explanation for these observations. Nickel tetracarbonyl is a volatile organometallic compound that could form under specific chemical conditions and decompose when heated, releasing both nickel atoms and carbon monoxide. This mechanism could explain both the unusual nickel chemistry and some aspects of the carbon monoxide inventory detected by JWST. Mars orbiter opportunities around October 3rd provided a crucial observational window for validating these temporal evolution models. The geometry during Mars' closest approach offered the best combination of proximity and solar phase angle before 3I Atlas disappeared into poor observing conditions near perihelion. European Space Agency and NASA missions at Mars were positioned to observe 3I Atlas from approximately 30 million kilometers, closer than any Earth-based telescope could achieve. These observations could provide unprecedented spatial resolution of the coma structure and potentially detect compositional gradients across the nucleus surface. The activity timeline that emerged from months of observations showed a clear progression from dust-dominated early observations through the onset of water detection in late July, carbon dioxide domination in late August, and the appearance of optical emission lines in September. This sequence reflected both the changing observational capabilities as different instruments joined the campaign and the genuine evolution of the comet's activity as it approached the Sun. However, the temporal evolution also revealed important observational limitations and systematic effects. Different apertures, bandpass filters, and instrumental calibrations made it challenging to construct perfectly consistent light curves and production rate measurements. The most reliable comparisons required careful attention to observational methodology and instrumental effects. The steep production scalings observed for nickel and cyanogen set up clear expectations for the perihelion passage observations. If the temperature-sensitive release mechanisms continued to operate as 3I Atlas approached within 1.4 astronomical units of the Sun, the chemical activity should become dramatically more intense. But the temporal evolution also raised questions about the long-term stability of 3I Atlas's unusual chemistry. Would the carbon dioxide domination persist throughout the perihelion passage, or would increasing solar heating activate additional volatile reservoirs that could shift the chemical balance? The answer would provide crucial insights into the internal structure and composition gradients within this ancient interstellar visitor, potentially revealing whether its exotic chemistry extended throughout the nucleus or was confined to surface layers that could be stripped away by intense solar heating. Part 12. Consensus in the Chaos. After months of observations spanning the electromagnetic spectrum from ultraviolet to infrared, using facilities from ground-based telescopes to space observatories, a coherent picture of 3I Atlas began to emerge from the apparent chaos of contradictory measurements and unprecedented chemical signatures. The evidence stack pointed unmistakably toward a natural interstellar comet with an intrinsically carbon dioxide-rich volatile inventory. The JWST near-infrared spectrograph had provided the definitive chemical fingerprint, carbon dioxide dominating the gas production at an 8:1 ratio relative to water, accompanied by carbon monoxide, carbonyl sulfide, and crystalline water ice suspended in the coma. This wasn't a marginal detection or a model-dependent inference. The carbon dioxide emission blazed across multiple infrared bands with signal-to-noise ratios that left no doubt about its reality or abundance. When combined with the swift ultraviolet detections of hydroxyl radicals and the ground-based optical detections of cyanogen and nickel emission, the chemical portrait was internally consistent and observationally robust. The carbon chain depletion observed in McDonald Observatory spectra provided additional chemical constraints. The extremely low carbon-2 to cyanogen ratio placed 3I Atlas among the most carbon chain depleted comets ever observed, consistent with formation or processing conditions that could build carbon dioxide while suppressing more complex carbon chemistry. The nickel emission lines detected by the Very Large Telescope, occurring without corresponding ion signatures, implied distinctive release mechanisms that favored photon-stimulated desorption or mild thermolysis of nickel-bearing organic compounds. This was unusual, but not impossible within the framework of known comet chemistry processes. The distant activity detected by TESS recovery observations and confirmed by swift ultraviolet spectroscopy was entirely consistent with hypervolatile-driven or grain-driven sublimation processes. Carbon dioxide can sublime at distances well beyond 3 astronomical units, providing a natural explanation for the early activity onset without requiring exotic physics. The dynamical studies provided crucial context for interpreting these chemical anomalies. The kinematic analysis suggested an age of 3 to 11 billion years and possible thick disk origin, with chemical abundance patterns consistent with formation in low metallicity environments during the galaxy's early evolutionary phases. Size and radius constraints remained model-dependent but consistently pointed toward a nucleus several kilometers in diameter, comparable to, or larger than 2I/Borisov, and definitely larger than the estimated size of 1I/Oumuamua. This size range was entirely consistent with natural comet formation processes and the observed levels of gas and dust production. Crucially, there was no credible spectroscopic or photometric evidence requiring an artificial origin for 3I Atlas. The carbon dioxide domination, unusual metal chemistry, and other exotic signatures were unprecedented in solar system comets, but they remained within the bounds of natural chemistry and physics. The technological hypotheses that had been proposed in various preprints and commentary were not supported by the observational evidence available through October 2025. The JWST spectra showed molecular emission lines from known volatile species undergoing well-understood excitation processes. The VLT observations revealed atomic emission from metals being released through conventional sublimation or desorption mechanisms. This distinction was important for both scientific accuracy and public understanding. 3I Atlas was certainly exotic. Its chemistry was unlike anything previously observed in our solar system, but exotic didn't mean artificial. The universe is capable of producing natural objects with compositions and properties that challenge our expectations based on local experience. The consensus didn't imply certainty about every aspect of 3I Atlas's origin and evolution. Significant mysteries remained about the exact volatile layering within the nucleus, the physical mechanisms responsible for the unusual metal chemistry, and the detailed formation conditions that could produce such extreme chemical fractionation. The true nucleus size remained uncertain beneath the extended coma, requiring better point-spread function subtraction techniques or late-phase observations when activity levels decreased. The origins remained probabilistic rather than definitive. Assignment to the thick disk population was based on kinematic modeling with inherent uncertainties spanning billions of years. Post-perihelion evolution could still reveal additional compositional complexity or temporal changes that would modify the current chemical picture. The steep production scalings observed for nickel and cyanogen suggested that perihelion passage could activate previously dormant chemical processes or expose deeper layers of the nucleus with different compositions. But the observational foundation was solid. Multiple independent measurements using different techniques and facilities had converged on a consistent chemical portrait of carbon dioxide domination, water presence, unusual metal chemistry, and carbon chain depletion. This wasn't a case of a single anomalous measurement or model-dependent interpretation. It was a robust observational result that demanded explanation within the framework of natural comet formation processes. The comparison to previous interstellar visitors highlighted the emerging diversity of this population. 1I/Oumuamua had shown kinematic anomalies without detectable chemistry. 2I/Borisov had displayed carbon monoxide enrichment with otherwise conventional comet behavior. 3I Atlas exhibited chemical anomalies with perfectly normal kinematics. This diversity suggested that interstellar objects represent samples from a wide range of planetary formation environments and evolutionary histories. Rather than a single archetype, the interstellar visitor population appeared to encompass the full range of compositional and physical properties that result from billions of years of planetary system formation throughout the galaxy. The consensus picture of 3I Atlas as a natural but compositionally extreme interstellar comet set the stage for interpreting the remaining mysteries and planning for future observations of similar objects. The chemical exoticism was real, the formation implications were profound, but the physics remained grounded in well-understood natural processes operating under unusual conditions. Part 13. Lingering Mysteries. Even as astronomers reached consensus on 3I Atlas's basic nature as a natural interstellar comet with extraordinary chemistry, fundamental questions remained that would drive research programs for years to come. These lingering mysteries represented not failures of the observation campaign, but rather the natural boundaries of what could be determined from remote sensing of a rapidly moving target during a brief observational window. The most pressing question concerned the origin of the extreme carbon dioxide domination. Two competing hypotheses emerged from the JWST team's analysis: formation near a carbon dioxide ice line in the parent protoplanetary disk, or thermal processing of an insulated crust that preferentially retained carbon dioxide while allowing water to escape over geological timescales. Both scenarios remained plausible given the available evidence. Formation near a carbon dioxide ice line could occur in protoplanetary disks with different temperature profiles than our solar nebula, particularly around lower mass stars or in systems with different disk structures. The thick disk origin suggested by kinematic analysis was consistent with formation around stars with different properties than our Sun. Alternatively, billions of years of interstellar travel could have created a differentiated nuclear structure with carbon dioxide-rich interior regions insulated by refractory surface layers. Cosmic ray processing, thermal cycling, and interactions with the interstellar medium could potentially concentrate volatile species in specific regions while depleting others. The cause of the severe carbon chain depletion represented another fundamental mystery. Was this a primordial signature reflecting formation conditions in a carbon chain-poor environment, or the result of processing that preferentially destroyed complex carbon molecules while preserving simpler species like carbon dioxide? Understanding this distinction was crucial for interpreting 3I Atlas's formation environment. If the carbon chain depletion was primordial, it suggested chemical conditions during planetary formation that don't exist in modern star-forming regions. If it resulted from processing, it could provide insights into the chemical evolution that occurs during extended interstellar travel. The nature of the nickel release mechanism remained poorly understood despite the clear observational evidence for nickel emission without corresponding ion signatures. Direct sublimation of metallic phases was ruled out by the abundance ratios, but the specific organic or nanophase host materials responsible for the nickel release couldn't be identified from remote observations. Future coordinated infrared and optical campaigns during perihelion passage could potentially identify the carrier phases responsible for nickel release. Simultaneous observations of metal emission lines and organic molecular bands might reveal correlations that could distinguish between different release mechanisms. The grain physics governing the extended water production remained mysterious. The swift ultraviolet detections and Yang infrared observations had provided evidence for large icy grains carrying water ice through the coma, but the detailed sizes, lifetimes, and compositions of these grains couldn't be determined from existing observations. Multi-wavelength monitoring during perihelion approach could potentially constrain grain evolution processes and determine whether icy grain sublimation was indeed the primary source of water production at large heliocentric distances. Such observations would require careful coordination between ultraviolet, optical, and infrared facilities. The possibility of activity, variability, and outbursting represented another unknown that could fundamentally alter the chemical picture. The steep production scalings observed for nickel and cyanogen suggested highly temperature-sensitive processes that could become explosive near perihelion. Analogies with unusual solar system comets like C/2016 R2 suggested that compositionally extreme objects could exhibit dramatic activity variations. Outbursting could expose deeper layers of the nucleus with different chemical compositions, potentially revealing whether the exotic chemistry extended throughout 3I Atlas or was confined to surface regions. Such events could also provide insights into the internal structure and volatile distribution within the nucleus. The true nucleus size remained uncertain beneath the extended coma that had dominated all observations since discovery. Better point spread function subtraction techniques or late-phase observations when activity levels decreased could potentially provide direct constraints on the nuclear dimensions and surface properties. Size constraints were crucial for understanding the mass budget and evolutionary timescales for 3I Atlas. A larger nucleus could sustain current activity levels for longer periods and potentially maintain unusual surface chemistry through multiple thermal cycles. A smaller nucleus would require more efficient volatile release mechanisms and shorter evolutionary timescales. The origins question remained fundamentally probabilistic rather than definitive. While the kinematic analysis strongly suggested thick disk membership and ancient age, individual source star identification was beyond the reach of current observational capabilities. The assignment to specific galactic populations carried confidence intervals spanning billions of years and thousands of parsecs. Future astrometric observations with extremely high precision could potentially refine the orbital determination and reduce uncertainties in the kinematic analysis. However, the fundamental limitation was the chaotic nature of galactic dynamics over geological timescales, which prevented definitive source identification even with perfect observational data. Comparative planetology questions offered promising avenues for future research. How did 3I Atlas's extreme chemical ratios compare to other unusual solar system comets like C/2016 R2? Could similar formation or processing mechanisms explain both interstellar and solar system compositional anomalies? Building a statistical sample of interstellar object compositions would be crucial for distinguishing between formation and processing explanations for compositional anomalies. The Rubin Observatory's upcoming survey capabilities offered the best hope for discovering sufficient numbers of interstellar visitors to enable population studies. Data gaps remained that could still be filled during 3I Atlas's current apparition. Mars orbiter observations around October 3, 2025, offered the best spatial resolution and photometric precision before the comet disappeared into poor observing geometry near perihelion. The Psyche spacecraft's flyby opportunity and potential JUICE observations could provide additional constraints on coma structure and composition. These remaining observational opportunities represented the final chances to constrain 3I Atlas's properties before it departed the inner solar system forever. Unlike solar system comets, which return on predictable schedules, interstellar visitors offer no second chances for follow-up observations or refined measurements. The lingering mysteries weren't failures of the observation campaign, they were natural consequences of studying a rapidly moving target during a brief observational window using remote sensing techniques. 3I Atlas had revealed more about its composition and origin than any previous interstellar visitor, but fundamental questions about formation mechanisms, internal structure, and evolutionary history would require different observational approaches or larger statistical samples to resolve. These mysteries represented the cutting edge of interstellar object science, defining research programs that would extend well beyond 3I Atlas's departure from the solar system. Each unanswered question pointed toward observational capabilities, theoretical developments, or statistical analyses that could advance understanding of planetary formation processes throughout the galaxy. The fact that so many fundamental questions remained open after months of intensive observations with the world's most sophisticated telescopes highlighted both the complexity of these ancient visitors and the challenges of studying them with current technology. 3I Atlas had pushed observational capabilities to their limits while revealing tantalizing glimpses of chemical processes and formation environments that operated billions of years ago in distant star systems. Part 14. Looking Ahead. The story of 3I Atlas was far from over as it approached perihelion in late October 2025. In many ways, this interstellar visitor represented not an ending but a beginning, the opening chapter in a new era of interstellar object science that would transform our understanding of planetary formation throughout the galaxy. The Rubin Observatory, still in its commissioning phase during 3I Atlas's discovery, offered a glimpse of the revolutionary capabilities that would soon be available to astronomers. Rubin's combination of wide field coverage, deep sensitivity, and rapid cadence promised to increase interstellar object discovery rates by orders of magnitude once the legacy survey of space and time began full operations. Conservative forecasts suggested that Rubin could discover dozens of interstellar objects per year, with some models predicting detection rates approaching 100 objects annually. This dramatic increase would transform interstellar object science from a field focused on individual case studies to one capable of statistical population analyses. Population statistics would be crucial for testing the formation and evolution hypotheses that had emerged from 3I Atlas observations. Was the extreme carbon dioxide enrichment typical of thick-disk interstellar objects, or was 3I Atlas a rare outlier? Did carbon chain depletion correlate with inferred age or galactic origin? How common were unusual metal abundance ratios in the broader interstellar visitor population? These questions could only be answered with large statistical samples that would become available as survey capabilities improved. The transition from individual discoveries to population studies would mark a fundamental shift in how astronomers approached interstellar object science. Spacecraft mission concepts were already being developed to take advantage of improved discovery timelines. Eubanks and collaborators had outlined a multi-platform observation strategy that could coordinate observations from the Psyche asteroid mission during its September 4th flyby, Mars orbiters during the October 3rd close approach, and the JUICE-Jupiter mission during its November 4th observation window. The Mars encounter offered particularly promising opportunities for high-resolution imaging and spectroscopy from approximately 30 million kilometers. European Space Agency and NASA missions at Mars carried sophisticated cameras and spectrometers that could provide unprecedented spatial resolution of 3I Atlas's coma structure and potentially detect compositional gradients across the nucleus surface. These observations could help resolve fundamental questions about the distribution of volatile species within the nucleus and the physical processes driving the unusual chemical signatures observed from Earth-based telescopes. Multi-platform observations could also provide valuable experience for coordinating future interstellar object encounters. The broader implications for astrobiology and technosignature research were already being discussed in the scientific literature. While 3I Atlas showed no evidence for artificial origins, the observation campaigns had demonstrated capabilities for detecting unusual chemical signatures that could potentially distinguish technological from natural origins in future discoveries. Review papers and white papers were defining observational strategies for recognizing potential technological signatures while avoiding the false positives and confirmation biases that could lead to incorrect interpretations. The experience with 3I Atlas had highlighted both the power and limitations of remote spectroscopic observations for characterizing exotic objects. Pipeline development was proceeding rapidly to handle the expected flood of discoveries from next-generation surveys. Test-style recovery techniques, combined with Rubin's alert system, would enable much earlier detection and characterization of interstellar visitors. Automated spectroscopic follow-up systems could provide rapid compositional classification for newly discovered objects. Public communication strategies were being refined to emphasize the scientific importance of interstellar objects while maintaining appropriate skepticism about exotic interpretations. The experience with 1I/Oumuamua and 3I Atlas had highlighted the importance of clear messaging about observational uncertainties and the distinction between measured properties and speculative interpretations. Educational outreach programs were already incorporating interstellar objects as examples of how astronomy enables sampling of distant planetary systems without the need for interstellar travel. These cosmic visitors offered unique opportunities for comparative planetology on galactic scales, providing direct samples of building materials from star systems that formed under different conditions and at different epochs. The technological development pipeline was being adapted to meet the observational challenges posed by interstellar objects. Improved pointing systems for rapid target acquisition, specialized software for moving object spectroscopy, and coordinated observation scheduling systems were all being developed to maximize the scientific return from brief observational windows. 3I Atlas had demonstrated that interstellar visitors could carry compositional information that challenged fundamental assumptions about planetary formation processes. Future objects might reveal even more extreme chemical signatures or physical properties that would further expand our understanding of how planetary systems form and evolve throughout the galaxy. The transition from discovery-driven to survey-based interstellar object science promised to revolutionize multiple fields of astronomy. Galactic chemical evolution, planetary formation theory, astrobiology, and even fundamental physics could all be informed by statistical studies of interstellar visitor populations. As 3I Atlas continued its journey toward perihelion and eventual departure from the solar system, It left behind not just scientific papers and observational data, but a transformed field of study. The techniques developed, the questions raised, and the capabilities demonstrated during its brief visit would shape interstellar object research for decades to come. The universe had delivered a messenger from the distant past, carrying chemical information about planetary formation processes that operated when the galaxy was young. The message had been decoded, the chemistry understood, and the implications recognized. Now the challenge was preparing for the flood of additional messages that would soon arrive as observational capabilities reached maturity. Part 15. Resolution. Here's the result. After months of coordinated observations spanning every major astronomical facility on Earth and in space, after analyzing spectra from ultraviolet to infrared wavelengths, after developing new techniques for studying rapidly moving targets and interpreting exotic chemical signatures, the scientific community reached a remarkable consensus about 3I Atlas. This interstellar visitor was best explained as a natural comet with an extraordinary chemical composition that challenged every assumption about how these icy building blocks of planetary systems form in the cosmos. The carbon dioxide domination, 8 times more abundant than water, placed it in a compositional class essentially by itself among all known comets, solar system or interstellar. The JWST near-infrared spectrograph had provided the definitive chemical fingerprint that transformed 3I Atlas from a puzzling dust-dominated object into one of the most chemically exotic comets ever observed. Carbon dioxide blazed across multiple infrared emission bands, accompanied by water vapor, carbon monoxide, carbonyl sulfide, and crystalline water ice, a molecular cocktail unlike anything in our local cosmic neighborhood. The VLT observations had added layers of chemical mystery with the detection of numerous nickel emission lines, while iron remained stubbornly undetectable. This unusual metal chemistry, combined with the late August appearance of cyanogen and the severe depletion of carbon chain molecules, painted a picture of fractionated chemistry that suggested formation or processing conditions unlike anything in our solar system. The swift ultraviolet detections had revealed that water was indeed present and active, but as a minor component of a volatile inventory dominated by more exotic species. The hydroxyl production rate of approximately 40 kilograms per second was impressive for any comet, but it paled in comparison to the carbon dioxide production rates inferred from infrared observations. What had changed astronomers' minds about 3I Atlas was the progressive revelation of its hidden chemistry as different instruments joined the observation campaign. The early optical spectra had suggested a dust-dominated, gas-poor object, a reasonable initial interpretation given the available data. The swift ultraviolet observations had revealed significant water production, shifting the narrative toward a more conventional comet with distant activity. But JWST's infrared spectroscopy had revolutionized understanding by revealing the dominant carbon dioxide component that had been invisible to optical and ultraviolet observations. The late August detection of cyanogen and nickel emission lines had added further layers of chemical complexity that defied simple explanations. The technological hypotheses that had been proposed for 3I Atlas could be definitively retired based on the accumulated observational evidence. There was no credible spectroscopic, photometric, or kinematic evidence requiring an artificial origin at any stage of the observation campaign. The carbon dioxide emission showed all the characteristics expected from natural sublimation processes responding to solar heating. The metal emission lines exhibited the temperature dependence and spatial distribution consistent with thermal desorption from organic or mineral phases. The overall activity patterns followed the power law scalings typical of comet chemistry responding to changing solar illumination. The alien hypothesis wasn't necessary to explain 3I Atlas. Natural processes operating under unusual conditions were entirely sufficient. The challenge wasn't explaining how the object behaved, but rather understanding where and when such unusual chemistry could arise through conventional planetary formation processes. The kinematic analysis had provided crucial context by suggesting an ancient origin in the galaxy's thick disk population, possibly dating back 8 to 11 billion years to an epoch when star formation occurred under chemical conditions significantly different from today's environments. This temporal perspective transformed 3I Atlas from an inexplicable anomaly into a comprehensible relic of ancient planetary formation processes. The formation implications were profound. If 3I Atlas truly represented typical building materials from the galaxy's early phases of planetary formation, it suggested that terrestrial planet formation throughout cosmic history had access to chemical inventories systematically different from our solar system's composition. The outstanding mysteries, the exact mechanisms of carbon dioxide concentration, the nature of nickel-bearing phases, the causes of carbon chain depletion, remained areas for future research rather than fundamental challenges to the natural formation hypothesis. These were questions of detailed chemistry and physics rather than basic astrophysical principles. The planned Mars orbiter observations and potential post-perihelion follow-up could still refine understanding of 3I Atlas's composition and structure. But the fundamental nature of the object was no longer in doubt. It was a natural interstellar comet carrying chemical information about planetary formation processes that operated billions of years ago in distant star systems. The context provided by previous interstellar visitors highlighted the emerging diversity of this population. 1I/Oumuamua had shown kinematic anomalies without detectable chemistry. 2I/Borisov had exhibited carbon monoxide enrichment with otherwise conventional behavior. 3I Atlas displayed chemical extremes with perfectly normal kinematics. 3 objects, 3 distinct personalities, suggesting that the interstellar visitor population encompasses the full range of compositional and physical properties that result from planetary formation throughout the galaxy's history. No single archetype could capture this diversity. Each visitor carried unique information about its formation environment and evolutionary history. The broader significance extended far beyond 3I Atlas itself. Each interstellar object represents a free sample return mission from distant star systems, carrying direct physical evidence about planetary formation processes that operated light years away and billions of years ago. These visitors enable comparative planetology on galactic scales without requiring interstellar travel. The chemical exoticism of 3I Atlas demonstrated that the universe's capacity for creating unusual but natural objects far exceeds our expectations based on local experience. The cosmos is vast, ancient, and creative in ways that consistently surprise and challenge scientific understanding. As 3I Atlas continued toward perihelion and eventual departure from our solar system, it left behind a transformed understanding of interstellar object diversity and planetary formation processes throughout galactic history. The fragment of another star's workshop had indeed told its secret, a story written in carbon dioxide and ice, preserved across billions of years of interstellar wandering. The universe had spoken in an alien chemical dialect, and humanity had learned to listen.